morning and welcome to the Morrison Planetarium Facebook page and the Open Space YouTube channel presentation of our Friday Cosmic Conversation. My name is Ryan Wyatt. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and it's a great pleasure to be joined today by Robert Hurt, Visualization Scientist at Caltech IPAC, which stands for the Infrared Processing and Analysis Center.
Well, it used to.
And now it's just IPAC.
Now it's just one of those acronyms because we do so much more now, so much more.
There's a whole spectrum of light that goes beyond that. But we are actually going to be talking about infrared light today, so the I in IPAC at least makes sense today. And
yes.
And actually, I should say welcome back to Robert, because he was actually our first guest on the Cosmic Conversations when we launched it back in May. We're both younger and more innocent and thought maybe we'd be doing this online stuff for a couple months or something. But now, thank you for joining us. Not quite a year later, but
well, now you clearly got all the bugs worked out of this process, right?
Exactly. Yes. So take two. Today we're going to be talking about infrared astronomy, and we're going to be using the cool and awesome open space platform to talk about some of this. And I'll just note that toward the end of the program, we'll be sharing a link to a survey, because OpenSpace is an open source software platform that is being funded in part by NASA. And so we're interested in your feedback. And although a lot of things in OpenSpace you can just download the software yourself and do, we're actually using a few like bespoke elements today. So not everything you see today will be in the released version of the software, but who knows, maybe in a future version. So at any rate, we're beginning our little journey today looking at the Spitzer Space Telescope. And we talked about the IPAC acronym, but maybe it's a good chance to talk a little bit about the amazing Spitzer mission.
Absolutely. And first, also, let me apologize. As the world that we live in now, I am about a quarter of a block away from a massive construction site. So if you hear weird background noises, it's not me. I'm sorry. we live in the acoustic environments we kind of have to live in now. So yes, this is basically a wonderful chance for me to talk about some of my absolute favorite things, which is spaceships and cool imagery and infrared light, different ways of looking at the world around us. So I'm just thrilled to be here. And of course, for the past, actually now over 17 years, I have been working on NASA's Spitzer Space Telescope project since before it launched in 2003. And this was NASA's flagship mission to study infrared light. It's a companion mission to the Hubble Space Telescope in visible light, to the Chandra X-ray Observatory and X-rays, and to the Compton Gamma Ray Observatory, which concluded its mission a while ago studying gamma rays. So the idea was to have telescopes spanning the entire spectrum of light in order to give us access to the full range of phenomena out there to study, because you can't just, if you really want to understand the universe, you can't restrict yourself to one narrow little slice of the electromagnetic spectrum. So Spitzer, I think personally, maybe a little vested, I think it's the coolest of all the great observatories. I think it just has the most rakish look. I love the sort of two-tone paint job with the nice astro stripe black on one side and reflective surfaces on the other. Beautiful.
I should know that we imported this model and couldn't get all of that like glorious texturing correct. So I'll note that you should probably, if you want to go and look online on the Spitzer website, you can get a better sense of what the telescope looks like, because that paint job was actually really important to the continuing success of the mission.
No, yeah, it was a mission that was literally made possible by really good paint, if you can wrap your brain around that, because Spitzer had to be designed in a way that it was itself a heat pump acting to cool itself off. And so what you can't see in this simulation is that surface, that black, what looks like a black shiny surface. If you actually could see Spitzer in person, that surface is absolutely jet black, no hint of highlight, shine, shimmer, any reflected light. It is like one of the blackest blacks that you can see. And that's really important, because black surfaces, they definitely heat up if you shine light on them. But the converse of that is they actually radiate heat out also very, very effectively. There's a term called a black body, and we'll come back to that later when we're talking more about the astronomy. But basically, by painting all the surfaces that point away from the sun black, that meant Spitzer naturally just pumped heat out with no electronics, no activity, passively, in addition to the things that we put on board to keep it cool. And of course, you see there's this big solar array on the back side, and which is attached to a panel. That's all designed both as a way of collecting power for the telescope, but as a heat baffle to keep light from the sun from heating up the barrel. And it only attaches down at the bottom where the spacecraft electronics are, and at the very base there's a covered radio dish used for communicating with Earth. But one of the things that made Spitzer possible was its location. It was the first astronomical observatory class mission that was sent into space, not in Earth orbit, but basically flung out into its own orbit around the sun. And so as we zoom away from Spitzer and let it dwindle to a tiny dot, we will actually be seeing where Spitzer was at the end of its mission, which was concluded in January 30th, a year ago. Fortunately, right before all the COVID hit us, so we got to have a big party as we said our farewells to Spitzer. But on that date, Spitzer was in its own orbit around the sun, and if we keep zooming out, eventually we will see where the Earth is relative to Spitzer. You will see that that's the Earth, and you'll notice Spitzer's orbit lines up almost exactly with the Earth's orbit, and that isn't an accident, right? Spitzer was launched from Earth, but it was kicked into a slightly larger orbit. And as a result, it takes Spitzer just a little bit longer to go around the sun than the Earth does. So we call that an Earth trailing orbit. And that Earth trailing orbit basically lets Spitzer just drift away from the other really big source of infrared contamination, which is the Earth. So if you basically take an infrared telescope and leave the Earth behind, then you don't have to worry about the glow of the Earth heating up your telescope and making it difficult to observe.
I guess it makes it difficult to go out and repair it, but other than that.
Well, and that's the other thing. It had to be very carefully designed. There were no Hubble servicing missions for Spitzer for its 16-plus year mission. And remarkably, it actually operated flawlessly for over 16 years without any upgrades other than those that we could send by software. And there were very significant upgrades that were made actually to Spitzer over time. But if you sort of look where Spitzer is and you look where the Earth is, you can see this is actually the reason that Spitzer eventually had to shut down, even though it was working quite nicely. In order for Spitzer to point at Earth, as it gets further and further behind the Earth, it actually has to tilt more and more towards the sun. And so it actually was getting to a point where its solar arrays had to tilt at such an angle, they were no longer getting enough power to keep it power positive, and we were dipping further and further into the battery reserves. So the same thing that made Spitzer possible to do everything that it did, to have a passive cooling system, was the thing that sort of had its built-in end date. And that end date, I will note, ended up being many years later than any of us had really suspected at the end of the mission, largely because people getting really, really clever about how we can conserve power, how we can continue operating literally outside of the design specifications. Our last software update to Spitzer, we actually had to send it instructions to tell it not to shut down when we observe certain things, because it actually had to tilt so far out of its safety zone to point to Earth, that would have triggered a shutdown before we'd updated the software. So we called that part of the mission Spitzer Beyond, because we were literally operating beyond the design limitations of the telescope. So I think that's a really good success story.
Yeah, that's amazing.
But we've been talking about infrared as a telescope, and the question of why do we want an infrared telescope? And we have this beautiful star field that we see in the background in open space, which is the way our eyes see the universe. But the thing is, starlight is almost entirely coming from the few hot stars that are out there. When we go further into the infrared, we see a whole new universe emerge. This is the universe is seen at 100 microns. So this is the longest infrared wavelength that Spitzer would detect. And we see that all that, what we think of as empty space between the stars, is actually filled with dust. It's also filled with gas. And what Spitzer does by observing in the infrared, it has access to the thermal glow of dust and objects that are actually a lot cooler than stars. I mean, historically, we talk about, you've probably heard that like infrared light is like heat radiation. And it's both accurate but not accurate, because it turns out it's no more or less heat radiation than visible light is. It's just that visible light is the heat radiation of really hot things that are thousands of degrees. And that's where things like the sun peaks, like or a filament in like a halogen light bulb, that peaks thousands of degrees, and so it puts out mostly visible light. When you cool yourself down to hundreds of degrees above absolute zero, then you actually start putting out most of your energy in the infrared. And so that's what happens here. That's why we suddenly see all of these incredible dust structures throughout the Milky Way. We are actually inside the disk of our galaxy, or like a big flat pancake, and we're sort of looking around in all directions, and we're sort of seeing through all that haze, and it builds up to this incredibly bright feature that's just, you know, dust all the way from like very nearby neighboring dust all the way through to the other side of the galaxy. And that's something that Spitzer was able to do. We could see through dust that normally was blocking our view all the way to the other edge and see what its geography was, see where it clumped together to form stars. But then Spitzer also could access shorter wavelengths of infrared light. And so if we transition to another infrared image of the sky, but this time in what we call the near infrared wavelengths, that are just maybe twice as long as visible light wavelengths that we look at, not quite. Then we see this view from the 2-micron all sky survey, which is the project I worked on before I started working for Spitzer. So I love this data set too. It turns out this is actually even shorter wavelengths than Spitzer could see. But
Right.
the thing I want you to notice here is that you see the galaxy, the Milky Way, just still all the stars are so visible all the way through the center. If I had to ask you, where's the center of the Milky Way, you would look at that and have absolutely no problem finding it. But if we were to look in visible light, it's just lost in that muck of dust in the foreground.
Right.
That's because not only does dust glow with a thermal glow when you get to longer wavelengths of infrared light, dust also, so right here, this is the visible light view, and you see all of these obscuring dust clouds are blocking our view. Infrared lets us peer through and get to things we couldn't normally see.
And so then when we look at like the 2MASS image here, we still see some evidence of that dust. We still see some, to be the sciencey term, occlusion, or some of that dust blocking light from more distance. So is this like the densest clumps of dust, or what's going on?
Yes, exactly. As you push further into the infrared, basically what happens is it's almost as simple as thinking like, if you have a dust particle that's this big, if the wavelength of your light is that big or smaller, it tends to get blocked by it. But if the wavelength of light gets longer, that dust particle becomes less and less of an obstacle. And so effectively, you end up penetrating more and more of the dust. And as you go to longer and longer wavelengths, it's like that dust just kind of melts away. And only the very densest region, where you're passing through the largest quantity of dust, it still kind of blocks your view slightly. But by the time you get to the wavelengths that Spitzer sees, which is slightly longer than these, most of that has even gone away. And you're really just getting a clean view of the stars with some of that dust beginning to glow in its hottest temperatures. So it really gives this amazing view of the universe that you just can't see in visible light.
And I think we have a good example of that within a galaxy, or maybe you're not ready to go there yet.
Well, no, actually, I was going to make that exact comment, right? Because, you know, this is what a galaxy looks like if you live in the middle of it, right? And you're trying to look out. It's kind of like being dropped in Times Square and being asked to draw a map of all of Manhattan. Right. It's like you can do a really good job nearby, but like how far down is that building down? It's really hard to tell. Is it a big building that's really far away, or is it a small building that's close up? Right? You can't. It's hard to make that judgment. So if you look at other galaxies from the outside, like similar to the Milky Way, this is a visible light view of the Whirlpool galaxy in 51. And so you can actually see some of these same factors, these same effects going on. You see these dark dust lanes that are blocking our view of some of the stars there. You actually also see that there are, the visible light here is actually being dominated by the very hottest, brightest stars, which are actually very few in number. There are actually a lot more small, dim stars that put most of their energy out in the infrared than the handful of bright ones that put most of their energy out in the blue or the ultraviolet. But a star that's only 10 times more massive than the sun can actually put out 10,000 times as much light. And so in visible light, you actually get really biased towards the bright stuff, the young stars, the hot stars.
So these are like the social media influencers of the galaxy. So they're like a small number that's like outsized impact on the.
You drew that right back to everything that's destroying civil discourse today. It's like, I mean, I don't want to shame visible light, but really you're letting yourself get influenced by the views of a few very loud stars that aren't necessarily representative of the full galaxy.
Right.
For that, you want to go to the infrared view, and so two things are going on here. First of all, the starlight becomes a much more uniform representative sampling of the total survey of stars in the galaxy, not just the big ones, but the small ones as well. And so in a way, it actually gives you a much more direct measure of the mass of the galaxy in stars. But then the other thing that, of course, happened is now we see these incredible spiraled, spoked patterns of red. That is the dust clouds, the things that were blocking our view of invisible light, but now starting to glow and stand out and give us this incredible access to that structure of what's going on. And the dust is interesting because it actually traces the gas, which is even harder to observe until you get to things like radio light. And wherever the gas is getting dense, you will tend to form dust particles. And so this actually gives us a sense of this whole other component of the gaseous component of a galaxy and where its density is building up to the higher and higher levels, because that's exciting, because that's when you get to a point that finally clouds of gas and dust clump off because their own gravity overcomes their ability to sustain themselves, and they actually start to collapse and they become star-forming regions. And these are the beautiful nebulas that give rise to all the stars that you see in the galaxy. At some point or another came through one of these dense clouds that was a star-forming region earlier in its history.
And so the color coding here is actually kind of similar to what we saw when we were looking at the whole sky, where it's like this, the red stuff here is that like the 100 micron, like where we're seeing the dust that was sort of surrounding us in the galaxy, and the blue part of the image is more of the starlight.
Yeah, exactly. And it's in these images, typically the ones I've worked on for Spitzer, what I've tried to do is maintain the relative ordering of the colors when I make the final image. That, in blue light has has a shorter wavelength than red light. And so the things that are blue come from short wavelength, the things that are red come from long wavelength. Well, if we just shift that proportionality into the parts of the spectrum we can't see, we try to maintain that same order. So the blue light here is the shortest wavelength of the infrared light that Spitzer sees, and the red is the longest. In this case, we're actually only looking out to about 8 microns. So this is like 1/10 the wavelength of that incredible dust map that we saw before. Right. And so it's only, and I just to be fair and be technical, the bulk of this glow, in fact, isn't coming from the thermal glow of the dust. It turns out there is a different kind of way the dust can glow due to basically fluorescence. These complex fractal carbon dust molecules, they can actually absorb ambient starlight from the stars, and then they actually re-emit light at very particular wavelengths of light around 6 to 10 microns. They're called polycyclic aromatic hydrocarbons. And so you actually need, they're not quite hot enough to be glowing thermally at 8 microns. These dust clouds are like 10, 20 degrees above absolute zero. They're really, really cold. And we only see them because then they also light up. When we go out to, say, twice as long a wavelength, like 20 microns or so, 24 microns, then these clouds actually begin to glow thermally. And then that becomes that other process.
Very cool. So these are kind of like atoms that are being jiggled in a very specific way so that they kind of resonate and emit at these.
Yeah, it's like those posters, I used to see back in my my ancient accessible youth at Spencer Gifts, when you'd go in and they'd have the room with the black light and all the fluorescent posters on the wall, and those posters would be absorbing the ultraviolet photons from the black light and re-emitting in vivid green and yellow and blue, and that's.
Wow.
And think of this as an infrared black light poster.
Give you credit.
I think those are still a thing, are they?
Yeah, I don't know how many of these we've done, but it is the first mention of Spencer Gifts in one of our cosmic conversations. But since we're bringing it back down to Earth, maybe this is a good chance to show some of the kind of amazing videos that you worked on quite a while ago now for an art exhibit. Yeah,
this was way back in 2008. The city of Pasadena would have these events called Art Walk, where they would get a collaboration between all the art institutes in the city, because art is a really big thing in Pasadena. And they would collaborate on a single theme and have events scheduled all over the city. Well, back in 2008, one of our group sort of had an in on that, and we actually proposed that we contribute in this art event as sort of a science outreach thing. I think it was the first time that a science institute had actually participated in Art Walk. The theme that year was skin, and it was sort of take this and run with it. How does skin? How does it affect our perceptions of one another, our biases? So there were dance pieces, there were concerts, there were photography exhibitions, all tied to this. We took that idea and ran with the idea of skin for red. because we thought it would be fascinating to show people how different the world they're so familiar with looks if you just look at it at a different part of the spectrum. In this case, instead of looking in the visible spectrum, we went out to about 10 microns, which is a wavelength of light that is sensitive to the thermal glow of things that are about the temperature of a human body. We are in the Kelvin scale. Our temperature is about 300 degrees Kelvin, and water freezes at 273 degrees Kelvin. And it turns out 10 microns, but once you get out to about 300 degrees, that's when things start to glow. And so we become luminous things at that. But yeah, I guess you can go ahead and pop up one of the so we did a lot of, it was sort of like photo studies. We would do photo studies of visible and infrared and try to contrast that and show things, how things might appear really dark in visible light. You might not see things, but in the infrared, you are your own source of light. So if you could see in the infrared, it wouldn't matter whether the lights are on. You would basically see people. This is why we use infrared cameras to look for rescue missions, to find people lost in the woods, or to look through dust or smoke. Another thing that's kind of cool about infrared, if we run this one, if you ever watch like Scooby-Doo cartoons, there's always like, put on the little goggles and you see the footprints that someone left behind. Well, if you're barefoot, you leave behind a thermal footprint, quite literally, on the ground. And we actually photographed someone just walking barefoot on a wooden floor. And when they do, you actually see the images, the footprint left behind, right? Again, thermal eyes. People couldn't sneak around barefoot. You'd be able to follow the trail for like a minute or two in the dark.
Always wear shoes if you're going to be sneaking around with them.
Exactly. You'd have to have not only sneakers that don't squeak, but they would have to have good thermal insulation to keep you from leaving a thermal trace behind too. Another one of my favorite pieces was showing off how something that we think of as transparent, like glass. I mean, glass, like this is what you put up if you want to see through things. Well, by the time you go out to 10 microns, glass is completely opaque. It blocks our view utterly. And so here's a picture of two colleagues, just normal picture, but in the infrared, you don't see the person behind the glass window at all, just gone. But if you were to touch the glass, if she were looking in the infrared, she might not see him, but she would see the sign of his handprint on the glass. I know, personally, this was my favorite. There was just something, I felt this just had a cool little story behind it. That, and you even see that you can even see the reflection of her in the infrared, as much as you would catch the hint of her reflection in visible light too. Because again, infrared light, it's acting just like visible light. It still reflects off surfaces. It mirrors still reflect it. But things that are so familiar to us can look very different in the infrared.
This does have sort of a horror show kind of like Donnie Darko, someone talking to you from the other side of the mirror quality to it, I have to say.
It does. And I think we have a few queued up for later that are even more horror show for incredibly innocuous reasons. But you know, so the crazy thing is that infrared technology, like so many others, has been developing so much over the past few years. And the images that you're looking at here, we actually had to spend something like $50,000 to get a camera capable of imaging these pictures at this incredible resolution of 640 by 480 pixels. Back then, that didn't sound quite as small because our monitors weren't quite as large, but still, right? It's insanely expensive technology. But what's crazy is that I can go for a couple $100. I can like buy a little thing I can plug into my phone now, and I can do the same thing. I can get those same pictures. That's a tiny fraction. And what's amazing is that it actually means that in some ways, infrared, the superpower of infrared light is actually something that's available without that crazy of an investment, right? It's cheaper than your phone for sure. And it does give you this superpower to see the world in ways that you can't normally see. And I keep this thing with me like all the time. When I was in Las Vegas, I was fascinated by popping this into the phone and looking at just how blindingly hot the streets were and how cold the humans were walking in front of it. Unlike the ones that we just saw, where we think of people as luminous. Well, if you're only around 300 degrees Kelvin, but the street is 330 degrees Kelvin, then you are the dark absorber and the street is the bright thing, It's all relative. Another thing I love to do, I hate cooking, but I found I get totally fascinated with watching things heat up using the infrared camera. Just seeing how unevenly your pan heats up versus, it's like, oh, that's why it's not cooking uniformly, because all the hot spots are over there. Or my favorite, watch pudding cook in the infrared. It looks just exactly like those images from Mauna Kea when the caldera was bubbling up and you had the lava crusting over, but hot bubbles popping up and glowing. It really makes something as dreadful as cooking even fun for even me. So,
well, I'm sure that's been good during the last several months.
Yeah. But kind of coming back to the skin infrared pictures, another one that we had popped up, and it would hit another really important theme, I think, for skin infrared, was the idea of the way that we perceive each other, the way we categorize people based on skin color and right. That all goes away in the infrared. Everything that we perceive as our bounding boxes between races, right? In the infrared, we all look the same. We all just glow. And in fact, if you were to racially categorize people in the infrared, it would probably be by like cold nosers or hot lippers, or people with cold ears versus hot ears, or frankly, people who love to wear sunglasses, right? Sunglasses, because glasses opaque in the infrared give people these really creepy dark eyes where the eyeballs are actually quite hot and thermal otherwise. So I think for skin infrared, this was probably one of the most powerful messages, that our whole perception identity, it's so just based on the accident of where our eyes happen to work in nature. What wavelengths of light did our sun glow brightest in? How did we biologically evolve to make use of that? But the other thing I love looking at the world in the infrared is how we interact with water. Okay, skip back a little bit. Let's go to. I think we had some shots of a hot tub.
The hot tub, yeah.
Because people just hang out in the hot tub, right? So if I were to ask like who was recently in the water or not in the water, it's kind of hard to tell looking visible. You might see droplets of water, but are those 10 minutes old or 2 minutes old? But hot tubs are cool because they actually look like pools of lava. And you see when people first get out of the hot tub, their skin is glowing hot. So if we had that ability to look in the infrared, we would see this. Now, another cool thing is like normal person just got out of the water, but just those little droplets of water cool his skin in a way that looks like, again, we if someone looked like that in visible light, we'd say, get to the doctor, man, there's something wrong with you. But something just as simple as a splash of water in the infrared takes on this incredible, creepy appearance. But then my other favorite sequence in this is a friend of ours, Whitney Clavin, just walking through the hall, trying to get a drink of water. I think if we jump in at like around 2:26, yeah. So we just took a few pictures of her, very innocent, sipping from a water fountain. What's weird about that? Well, aside from the fact in the infrared, it looks like she's drinking blood. She gets up, smiles. Nothing creepy about that, right? Nothing creepy. Of course, the funny thing is, if she were drinking blood, it actually wouldn't look like that at all in the infrared, because blood is quite warm, and so you would see nice warm things dripping until it cooled out, and then it would start to look dark again. But yeah, the infrared light really lets you just take some of the most normal day-to-day things, and it just transforms it into a completely different experience.
That's very cool. I have to say that is like the most Southern California physics education video that's like ever been made. Because if we did that in San Francisco, it would be, how quickly your body temperature drops when you walk outside on an afternoon and the wind whips you down to like, what feels like 10 degrees below zero. But no, it's
the streets of San Francisco would have a very different thermal profile than the streets of LA, that's for sure.
None of that Las Vegas problem with warm streets. Nope.
and we actually had that video running as part of this skin infrared art walk event. That was actually running in playing on a giant projection wall in downtown Pasadena for like a week, and we actually had an event there on astronomy visualization. So you and I were having dinner at a little cafe across the street from skin infrared running, and we would do live infrared camera demos. It was really cool. But I guess also the idea of doing like an art and science and education thing all wrapped up in a ball was also kind of very maybe feels very California, but I think it's cool.
Very cool. Well, and then I guess we could also bring this back to an astronomical phenomenon. So we're talking about sort of these warm objects in the universe. And we have a great data set in open space, sort of leaving our solar system behind to showcase where these sort of warm, not stars, but interesting objects called brown dwarfs are found nearby. We pull away fast.
Way far out now, right?
Yeah, exactly.
We're way too close to our system to.
Yeah, but we can just highlight the locations of those. If I give myself just a moment here.
Actually, yeah. Can you switch back to your? There we go.
Yeah. So we're kind of showing different types of brown dwarfs here. I don't know if you'd rather we could put a. I have the 2 mass up. I don't know if that makes it easier or harder to see.
Can you just switch back to the 3D stars? Yeah. That might be better, because then you can see how they're intermingled with, we have, when you've pulled this far away from the solar system, you actually are now floating in the 3D space of stars around the sun. And what's interesting is there is this class of object that is out there intermingled with them that is basically hidden from us. It was
right.
For many, many years there. That's actually really cool, because now you can see it's
a lot easier to
stars. And there are these dots that we have artificially brightened and made very fat so you can see them. Because if we were representing this in visible light, those would be lost. You wouldn't see them at all. They're far too faint. And that's because it's a class of object that lives in this kind of interesting never zone between things that are large enough to become stars. And maybe we can pull up that graphic too to demo this. On one side, when you get to things that are about 80 times as massive as the planet Jupiter, they have enough gravity to actually heat up and create nuclear fusion that sustains them as a star. So from like about 80 times the mass of Jupiter on up, you get stars. They glow, they generate their own heat. And then on the low end, from about 13 times mass of Jupiter and lower, we would call those planets. They tend to form in the solar system, orbiting a star, the way that the planets in the solar system form. But between those two ranges, between around 13 to 80 times Jupiter's mass, are objects that may have formed the same way as a star forms, by collapsing, by having a gas cloud collapse, and at the core, a dense object emerges, but not quite having enough mass to actually ignite nuclear fusion and be a self-sustaining source of energy. So these are weirdly kind of called brown dwarfs, because actually the one thing they aren't is brown. This is in fact, as astronomers, we are really terrible at naming things, especially when we use color in the name, because if I go down the list, white dwarfs actually aren't white, they're blue. Yellow dwarf stars aren't really yellow, they're white. Brown dwarfs aren't brown, they're red or they're magenta but anything but brown. Black holes, I guess, yeah, they're black.
They're pretty black.
Right, except that stuff glows around them. Is there anything we got right? Blue supergiants. Blue supergiants are actually blue. So, I guess if we name a dozen things with a color, once in a while we'll get one right. But they were named brown dwarfs because the smallest stars were called red dwarfs.
Right.
Of course, red dwarfs aren't really red. They're actually more orange. They're not cold enough to look red to our eyes in visible light.
And they weren't actually named before we found any of them, right? Like this was a term that was sort of, this kind of hypothetical objects that we hadn't yet discovered.
Yes. And they weren't discovered until I think it was around the early 1990s, because they're so small. They're only about the same size as Jupiter. They're not as hot as a star, and the bulk of their light's coming out in the infrared. So we actually needed to get to a point that we could build infrared detectors sensitive enough to identify these faint things. And then we have to be able to tell the difference. Is this something that's very faint, that's very close to us, or is it something that's bright, that's a long ways away? Because from Earth, it's very hard to tell. So you actually have to do things like wait till the Earth orbits the star and take images of the sky as the Earth goes back and forth. And then if you see something wobble back and forth just a little bit with respect to the background, then it's actually in the foreground, and you can figure out how far away it is. So you put all those pieces together, and you can start to actually figure out where there are really faint things that are infrared-only objects that fit the categorization of brown dwarfs. And this is we actually did a release back in January that was kind of cool. There was a project called Backyard Worlds that is a citizen science project that lets anybody who's interested in science go and look through these data sets and try to find the telltale signatures of these elusive cool brown dwarf objects. And what's amazing is that I think it was close to 50 of these were actually discovered by citizen scientists, and many others were reconfirmed, greatly expanding our data set of what our nearby not quite star, the population of not quite stars are in our neighborhood. I guess that's another Southern California thing. We only care about what the stars are, but the not quite stars, they haven't made it onto IMDb yet. So,
so the theme really is about a more egalitarian perspective on the universe, sort of being able to see stars and other galaxies that are.
It isn't just about being a star. You're just as important if you were a brown dwarf. A colleague of mine, Davey Kirkpatrick, who's one of the world's leading experts in brown dwarfs, we had a conversation recently, and he was saying he hates the term failed star. Yeah. Because this is like the classic way that I think brown dwarfs have been described. They're failed stars, as if the only thing that matters in existence is if you have reached the threshold of 80 Jupiter masses and ignite nuclear fusion. You are perfectly welcome to not ignite nuclear fusion. You are beautiful for what you are, regardless of your mass. So I think this is a case where even astronomy and astrophysics can give us a good lesson in context and identity. Be what you are, and be happy with it.
Well, very cool. I mean, we've actually been talking for about a half hour now. So if we have any questions, I should have noted earlier, please feel free to ask them in chat on Facebook or on YouTube, and we can answer those live. And ask and you shall receive. So are there technologies that can produce images of the universe in more extreme wavelengths, like microwave, more extreme in one direction, or gamma rays, more extreme in another?
Absolutely. In fact, before I moved into the regime of infrared astronomy, I was a radio astronomer, and in graduate school, I was working at things like the Very Large Array, made famous by Jodie Foster and Contact. Thank you, pop culture, for turning the places that we work into pop culture reference points. And so I was working both at longer wavelengths of radio, but also in the microwave region, the microwave and submillimeter region. And for that, I actually can thank another not quite so popular movie called The Arrival with Charlie Sheen. If you ever watched that movie, he was actually in the Caltech's Owens Valley Radio Observatory control room, where they had radio dishes that were designed to work in the microwave and submillimeter range of the spectrum. And you can sort of point a dish out and you get like a measurement of the spot in the sky, or you can actually take a series of radio dishes and have them sort of look at the crosstalk between them, and you can reconstruct images in the sky. There is an incredible array of these being built in Chile, the Atacama Desert in Chile, and I forget what the total dish count is now, but where you have these
6 dishes actually. And
okay.
I didn't plug this, but you can actually we have a show called Big Astronomy that we run every 11:30 in the morning every Wednesday on YouTube, on the Academy's YouTube channel called Big Astronomy, and we get to visit Alma in that. But yeah, it is this amazing capacity to take all of these individual antennas, which are huge on their own, and combine their observations to create these phenomenally high resolution images.
It's really amazing, and there have been some of the most incredible images out of that group in the last year of like actually showing the swirly, dusty disk of material around a young star, where you see like the shock waves and ripples that are the ripples from which we think planets are forming in these very young objects. Just some amazing imagery. And then for the gamma ray side, there was actually a mission. One of NASA's great observatory was the Compton Gamma Ray Observatory. Of course, as you get to the higher energy side of the spectrum, it's really hard because, in radio or in infrared, you have many photons that are all low energy. But by the time you get up to the gamma rays, every one photon of gamma ray has a lot of energetic punch to it. It takes a lot of energy just to make one photon. And so when you get to the X-rays or the gamma rays, you aren't really making images anymore. You're counting events right. One by one, and you try to localize. They came from over there, and again, we can actually Chandra X-ray Observatory does really good X-ray images. Compton actually did make a map of the sky, but much lower resolution because it's right. You have very few events, and you have to try to kind of correlate and figure out like a general direction. You can't. It's not as precise as having a big focusing mirror that gives you a really good image.
All right. Well, I don't know if we have any other questions. Do you want to just do a quick look at the glimpse before we head out?
Yeah, sure. I mean, we one of I think the most amazing things to come out of the Spitzer project in terms of imagery is the survey of our Milky Way galaxy with Spitzer in infrared light at very high resolution. Now, there are other missions like the WISE mission that surveyed the entire sky in the infrared, which is a phenomenal data set. In fact, is critical in the search for brown dwarfs as well as many other things. But Spitzer, because it had a larger mirror, was able to do what its science at much higher resolution, but it couldn't cover as much of the sky. So if we turn on the glimpse survey, we actually see the very central plane of our Milky Way here against the visible light view of it. And you can see how like all of those dust clouds, they just melt away and we see through it. And we mapped out sort of the 360-degree right narrow plane. And what it looks so tiny compared to what you see in this image, but again, remembering we live in a very flat disk, very, very flat disk that's very wide. It turns out that that little strip that you see actually contains, I believe it's over 80% of the Milky Way.
Crazy. Wow.
Because you're seeing the part where it gets flatter and flatter and shortened in the distance, right? That's like standing on in Oakland and looking out at San Francisco. The city, actually, you try to take a picture of it, you find out that very little of your camera frame is actually the city, right? It's falling into just a few dozen pixels right towards the middle. And
no matter how hilly it seems when you're biking around it, actually is pretty flat when you're looking from Oakland. Yeah.
Exactly.
Well, this is an amazing image, and I should just plug that we're using a different tool here to look at it called Worldwide Telescope, and we'll share a link in the chat. This kind of offers a different sort of perspective, I think, on some of the astronomical data sets that's, in general, more of a kind of two-dimensional view of the sky, but with this kind of deep exploration that you can do of some of these images.
And I have gotten lost exploring this data set so many times, and every now and then we'll go through this and pick out a particular region, and I'll make a new image of that really highlights that particular spot. But there's so much to see in here, and every one of these bright spots is a region where new stars are forming. There are these dark regions that are the very densest clouds, so dense that they're still actually opaque by the time you get out to 8 microns or even 24 microns. These are the regions that are going on. In fact, that particular object, we called that the snake. And if I don't think we have a good way to switch that to the glimpse MIPSCAL, but if you actually go to even longer wavelengths of infrared light and you look at that, you'll see these red dots embedded in the body of the snake.
Wow.
And those are protostars that are at the forming cores within that even at 10 microns, 8 microns, you can't see them yet, but they actually are starting to glow when you get to 24 microns. And that's one of the ways that we trace where the very youngest stars are forming. We look for these darkest dust lanes, and we try to probe inside that. And so when we look to the future, now we no longer have access to this part of the spectrum anymore with the decommissioning of Spitzer last year, but we're looking to the launch of James Webb Space Telescope later, and James Webb will finally restore our vision in the infrared part of the spectrum. James Webb is very much the successor, not just to the Hubble, but to the Spitzer Space Telescope, because it brings the idea of a very, very large mirror, a 4-meter mirror, compared to Spitzer only had like an 81 centimeter mirror. It was very small. It was very small compared to even Hubble's mirror. And as you go to longer wavelengths of light, that actually degrades the equivalent resolution you get for the same mirror. So we had much lower resolution images than Hubble, but we saw things that Hubble couldn't begin to see. James Webb is attempting to bridge the gap, make a mirror that's much, much larger so you get much sharper resolution, but continue to work in the longer wavelengths. So now we will get infrared images from James Webb that will be matching the resolution in visible light we can see with Hubble. And that becomes like you get sort of the best of both worlds. The whole new phenomenology you get in the infrared with the resolution that we kind of had learned grown to expect from Hubble. And then that's going to open up whole new areas of science where we can probe into these regions where stars are forming, but with a sharpness and clarity never possible before. So,
and to address a whole range of astrophysical questions, right? Because we touched on just a few things like star formation and these awesome, maybe not stars, but still lovely in their own right objects called brown dwarfs. But the other thing is, of course, that our universe is expanding, and a lot of the light that was emitted at visible wavelengths is now stretched into the infrared wavelengths. And so JWST is also going to reveal a lot of exciting stuff in cosmology too.
Yeah, no, looking at the earliest light in the universe and from some of the smallest, most distant objects with much better clarity. It's also infrared's all we didn't touch on at all, but infrared is critical for studying exoplanets. Right. And Spitzer made huge contributions in the study of exoplanets, which is a whole area of science it was never even built to be able to do. And it was only through like these clever software updates that it actually gained capabilities it didn't have before. It gained, we made its pointing more precise by an order of magnitude just by updating the software after figuring out what things caused vibration in the telescope. It was just amazing. And so all of that work that Spitzer did with exoplanets, James Webb will bring sharpness and sensitivity so that we're hoping to actually be able to characterize atmospheres of Earth-sized planets with it. So yeah, many cool things that'll be coming from that.
Awesome. Looks like we have another question about in the case of supernova explosions. Have you ever observed something specific in infrared versus X-ray or gamma rays?
Yes, the supernovas are actually really cool because it turns out that in some ways visible light is the least interesting way to look at them because the visible light only shows up in sort of the brightest shocks. So the youngest supernova where there's much more energetic material slamming into the area and lighting up in visible light. It turns out that those same shocks that aren't super visible in the visible spectrum can actually radiate and be incredibly visible in the X-ray spectrum. So the Chandra Observatory does these incredibly detailed maps of supernovas like Cassiopeia A or the Kepler supernova. But it turns out the same thing kind of happens on the other side of the spectrum. They actually light up, again, very vividly in the infrared as well. And so if you actually go panning through the glimpse survey that we were just looking at, particularly if you add in the 24 micron layer that we weren't looking at, supernova, those same shock shells tend to glow at 24 microns. And if you see anything that looks like a round spherical object, there's a good chance that was actually a shell of a supernova that occurred some point in the history of the galaxy. And in fact, there's a good one in that snake we were looking at. If we had the other version of it, there would be this thing that we called the egg. There was a round shell, and that was actually a supernova remnant that was actually sitting very close to it. So yeah, it turns out that infrared and X-ray pair really well. And looking at different wavelengths of X-ray and infrared, it actually lets you peel out the chemistry of what's going on. It actually literally lets you backtrack and sort of figure out how the star that blew up had layers of different elements due to the way that different kinds of fusion happen at different depths within the star, creating from hydrogen to helium to oxygen and carbon, ending up with iron at the core. And when those stars blow up, those layers actually get spit out asymmetrically. They go out in different directions, and you can actually map out, like here we see an overabundance of one element versus another, and it actually gives you a kind of like a CSI crime lab scene of how the star died, right? It's like, how did the guts splatter out after the guy was killed? Can you figure out from the pattern of how I see some liver over here and I see some intestine over here. It tells you a little bit about. Wow, I got morbid there.
I was just going to go with Dexter, but then you kind of went.
Dexter, right? You learn a lot coming to the crime scene after the crime happened by just being able to tell which part of your victim is on different parts of the room.
All right. Well, if we don't have any other questions, we'll give another moment here. But if not, thanks very much, Robert, for joining us today and sharing some insight into infrared astronomy and to share some of the cool artwork done for this infrared exhibit way back when. And we'll hope to see you maybe at some future online event.
Sure. I mean, I wish you the best of luck getting things reopened at Morrison. Just as my ending comment, I'd like to throw up reference to one of the projects that we're working on called Universe Unplugged. And it's where we actually do interviews kind of like this with astronomers with a focus on kind of career path and building. In addition to generating like videos, visualization videos that Frank Summers at Space Telescope heads up. So if you go to universeunplugged.org, you should find a fun collection of astronomy-themed visualization and conversation videos that tell more about our explorations of that. Is all part of NASA's science activation science activation program. That's the word I'm looking for. Program.
So we'll share a link to that in the chat. And as I mentioned at the beginning of the program, Open Space, coincidentally, also part of NASA's science activation program. If you've enjoyed having a chance to see some of the astronomical data that we showed in Open Space today, or if you're interested in exploring Open Space more, we'll share the URL to that as well to download the software if you want. And again, we have a survey if you'd like to fill that out about this experience of seeing astrophysical data in the context of our cosmic conversation. So thanks again, and thanks for joining us, everybody, both on Facebook and on YouTube, and we'll hope to see you next week.